Hello, everybody. Welcome to Ms. Maguire online video lecture. Today we're covering human genetics, and we will talk about chromosome abnormalities. Now, this lecture was divided into two parts. In the first part, I cover structure of chromosome and different type of human chromosomes. We talk about karyotype and other very important, interesting information. But today we will concentrate on abnormalities. Right, so let's go ahead and begin. But first, I want to remind you what karyotype is. I will go back and I'll show you a picture of karyotype. So karyotype is actually created when, let's say we have a person, we take his or her cell, and we extract chromosomes from a cell, and then we arrange them in a numerical order from a larger chromosome to smaller. And the picture will look similar to the one that you see on your screen right now. We have chromosomes 1, 2, 3, and so on. And chromosome 1 is largest one, and chromosome 22 is the smallest one. And we also have sex chromosomes. Now, if you look at this picture right now, you see that there is some abnormalities shown by this karyotype, because this person, and this is female because we have two X chromosomes. She has extra chromosome 21 that is called trisomy 21 or Down syndrome. So that's example of abnormal karyotype. Now, so why would abnormal karyotype even be seen in a people? What can cause abnormalities in human genetic makeup? That's the topic of today's lecture, right? So let's go ahead and begin. Okay. Now okay, here we go. So karyotype may be abnormal. Oops. Karyotype may be abnormal in chromosome number or chromosome structure. So either we do not have 46 chromosomes, because we as human, we have 46 chromosomes, 23 pairs. So if we have different number of chromosomes, like 45, for example, or 47, then it's considered to be abnormal karyotype by chromosome numbers, or it can be abnormal in chromosome structure. Abnormal chromosome accounts for at least 50% of spontaneous abortions, yet only 0.65% of newborns have them. Therefore, most embryos and fetuses with atypical chromosomes stop developing before birth. Many people are being diagnosed with chromosome abnormalities due to improved technology. So this chart summarizes abnormalities of chromosome. We can see abnormalities by numerical abnormalities and structural abnormalities. So the first is polyploidy, when we have multiple fertilization or diploid gametes that lead to extra set of chromosome. Polyploidy means we have, well, we as living organism like humans, I'm talking about Homo sapiens, we have two sets of chromosomes, 23 from a father and 23 from a mother. So if we would have one extra, then it would be polyploidy. Actually, it really never happened in human cells, because the human embryo would just not survive with polyploidy. But it might happen in some other animals, like in fish and salmon, or it can happen in plants. It's actually pretty common in plants, polyploidy. And euploidy, when we have extra chromosome or we're missing a chromosome, right? Now, structural abnormalities include deletion and duplication, translocation, inversion, dicentric and acentric chromatids, ring chromosome, and chromatripsis. And this is when several chromosomes are spontaneously shattered. Now we're gonna look at some of these abnormalities in more details, right? So let's go ahead and start with some examples. So the first, polyploidy. It's a cell with extra set of chromosomes. It can be a triploid, for example. Cells have 3 sets of chromosomes. They produce by fertilization of 1 egg by 2 sperm, for example. So if you have egg, and let's say this egg has 23 chromosomes, and when 1 sperm fertilizes egg, and what fertilization means, we have the sperm enters the egg and brings the genetic material, right? So it's a fusion of these 2 cells. So what would we have? We have 23 plus 23. That gives us 46. If we would have 2 sperms fertilizing the same egg, we would have 3 sets. So this is set 1, this is set 2, and this would be set 3. So the cell would have another set of chromosomes, right? That's what triploid is. Or fusion of haploid and diploid gametes. Now this means, so that's the egg and sperm. They're supposed to be haploid. Haploid means we have half number of chromosomes. So it should be 23, or I put 22 and 23. Now, what if during formation of egg, for example, chromosomes did not separate and we have 23 and 23, so we have 46. So this is called 2N. This is diploid egg. And if fertilized by haploid sperm, we still have triploid. Right, so that's our polyploidy. So polyploidy accounts for 17% of all spontaneous abortions and 3% of stillbirth and newborn death. Polyploids are common, however, as I already said, among flowering plants, or fish farmers raise triploid salmon. It never really possible in human babies, because if embryo or fetus is triploid, it will just not develop, right? Or it will not survive. So here you see abnormal karyotype that represents triploidy. So instead of 2 chromosomes 1, we have 3 chromosomes 1, we have 3 chromosomes 2, and so on. And actually 1 Y chromosome only over here. So that's just example how abnormal karyotype will look like if somebody has triploidy. And euploidy. So normal number of chromosome is called euploid. That's a normal. So if you put N in front of euploid, that means not normal, right? So it will be either 1 extra, maybe 2 extra, or missing some of the chromosomes. Now, what does it mean, this autosomal? Just want to remind you that we as human beings, right? So here I'm going to draw female, right? So here's my nice female over here with eyes, and she's smiling, right? We are diploid organisms. So if you take cells of her body, right, and you look at chromosome number, you will find 22 chromosome plus 22 chromosomes. Those are called autosomes. Now, why we have 22 and 22? Because this 22 came from her mother and this 22 came from her father. But it's only 44. Remember, we have 46. And then you would find, and again, where do you find it? In our cells. If you take my skin cell, my liver cell, my brain cell, and you look inside and count those chromosomes, you make karyotype. That's what you find, 22 and 22 chromosomes that called autosomes. And if it's a female, you will find X and X. So that's another pair. So 44, 45, 46. So total, plus XX, that give us 46 chromosomes, right? So those called sex chromosomes. So we have 22 autosomes and 22 pairs of autosomes and 1 pair of sex chromosomes. If this would be a male, we would have 44 plus XY. That also give you 46, right? So now if we have extra chromosome somewhere over here, let's say we have 22 plus 23, right? We call it autosomal aneuploids because we have extra or we missing these autosomal chromosomes. Then those fetus or embryo, they spontaneously aborted. Those that born are more likely to have an extra chromosome, trisomy, than a missing chromosome, monosomy. That means if we're gonna have an abnormal number of chromosomes, it's more likely for baby to survive if he or she has extra chromosome instead of missing a chromosome. So again, our normal is 46, right? So if somebody has 46 plus 1, right, that's called trisomy. So they more likely to survive. If somebody has 45 chromosomes, so we're missing 1, this is called monosomy. And this is very rare. This individual survive very rarely because you're missing a chromosome, you're missing too many genes, right? And this will affect a function of an entire organism. Now, how we get this aneuploidy? Well, you can get it because there is error in either meiosis or mitosis. Now, if it's error in meiosis, then, and remember meiosis, what meiosis does, meiosis produce eggs and sperm. Yeah, I know they don't want us to use word eggs, they want us to use word ova, but it just for purpose of better understanding, I'm gonna use female gametes, egg and male sperm. So meiosis is formation of egg and sperm. So if we have error during this formation of gametes, then gametes can be produced with extra chromosome, right? And another with missing chromosome. And this process is called nondisjunction, right? So when we produce one egg, so for example, we produce one egg with 45 chromosomes and another with 47 chromosomes, right? This is called non-disjunction. Now, during non-disjunction during meiosis can happen in the first part of meiosis. It's called meiosis 1, or second part called meiosis 2. Right, so now let's look how it is really different. And we're not going into detail over here. We're just gonna look at this picture and we see, so imagine this is a cell and the destiny of this cell is to become a sperm, right? So we wanna be this cell, where do you find it? You find the cell inside male testes. So inside the testes, we have those cells, they will divide to produce sperm. If it's a human cell will have 46 chromosomes, but only 2 chromosomes are shown over here, and it's a pair of chromosomes. Because we have, remember, we have 22 pairs. So we have chromosome 1, and chromosome 1 prime. We have chromosome 2, 2 prime, 3, 3 prime, right? So that's how they abbreviate them. For example, they show us, I don't know, chromosome 3, right? Maybe this is just chromosome 3 and chromosome 3 prime. Now, when we form eggs and sperm, these chromosomes need to be separated between daughter cells, right? So how it should be, one chromosome should go to this cell and one chromosome should go to this cell. But you see that didn't happen. That's what non-disjunction is. Instead, this cell over here get both pairs. Now, if you go back to human, we have 46 chromosomes, right? So this would have now, because we're supposed to split. So this supposed to have 23, right? So one cell supposed to have 23, and another cell supposed to have 23. But this now will have only 22, and this have 24. Right? And this one extra chromosome that's shown here, for example, in this blue color. Right? So that's meiosis 1. And then we continue to form a sperm. We need to go through one more division called meiosis 2. And you can see here that we produce sperm, and neither one is neither one has normal ploidy. So those cells missing one, right? Missing one, and those sperm has extra one, plus one, plus one. So if this is sperm, and now it's fertilized an egg, and in the egg, we're gonna show this chromosome in the pink color, right? So this is normal egg, but the sperm that fertilize now is missing one chromosome and has extra chromosome. If it's missing chromosome, it's gonna be monosomic. One chromosome is missing. If it has extra chromosome, we will have trisomic, one extra chromosome. So if the point here is that through meiosis, that is process of gametes formation. So we form gametes, eggs and sperm. If errors happen, and those errors called non-disjunctions, if chromosomes do not separate, then we will not produce normal gametes. And if it's happened in meiosis 1, that all gametes gonna be affected. Right? But if it's happened in meiosis 2, and again, we're gonna just look very quickly. In meiosis 2, so in meiosis 1, everything is fine. You see how one chromosome goes to one daughter cell, another go to another daughter cell. Now we need to split this chromosome into half, and this half called chromatid. So this one is fine, it's split normally, and this one did not. So it happened during meiosis 1. Now this cell is missing chromosome, and this cell has extra chromosome. And look, some zygotes can be euploid, so have a normal number of chromosomes here. So the chance is actually 50-50. 50% chance that the baby will develop with normal number of chromosomes, but 50% that baby will not. And out of this 50%, we will have 25% that it's going to be missing a chromosome, and 25% that it will have one extra chromosome. So that's what we talk over here. If this is this non-disjunction happens through meiosis, formation of gametes. But sometimes non-disjunction can happen through the mitosis. Okay, right, so but we now if it happened during meiosis, formation of gametes, right, then every single cell will be affected, because we all start with the first zygote. If it happens through the mitosis, that some cells might be affected, some might not be affected, called mosaic inheritance. Right. But now let's look what diseases can, example of diseases that arise from non-disjunction. So most autosomal and euploids cease developing long before birth. So it's going to be spontaneous abortion. Frequently seen trisomies in newborns are those of chromosome 21, 18, and 13. Carry few genes that are the autosomes, this chromosome 21, 19, and 13. That's why the babies survive, right? But look at the percentage of kids that will survive if they have extra chromosome 21, extra chromosome 18, or extra chromosome 13. Now, if somebody has trisomy 13, it's called Patau disease, right? Or Patau genetic condition. It's pretty rare. It's 1 in 12,500 or 21,000. So it's a pretty rare condition. Well, we don't know how often really this happened, because if it's resulted in abortion, for example, in the first 3 weeks, mother might not even know that she was pregnant. But we're talking about babies who are born, right? So that's babies who are born with extra chromosome 13. And percentage of survival 1 year after birth is less than 5%. And it's only 1 year after birth. So those kids will die, you know, very soon after they're born. If we have extra chromosome 18, trisomy 18, called Edwards condition, it's more common, but survival rate is also very low. And the most common trisomy that kids are actually survive are Down syndrome, extra chromosome 21. It's 1 in 800, 826. So it's a really very, very common genetic condition and disorder. And look, 85% of kids survive 1 year after birth. So Down syndrome are most common trisomy among newborns. People with Down syndrome have distinctive facial and physical problems. Edwards syndrome, due to non-disjunction in meiosis 2 in oocyte, and generally do not survive. And this is our trisomy 18. Serious mental and physical disabilities. Distinct features are oddly clenched fists. Next example of trisomy is Patau syndrome. Very rare and genetically do not survive, and generally, do not survive 6 months. Serious intellectual disabilities, great physical disabilities. Most striking feature is fusion of the developing eyes into one large eye-like structure in the center of the face, or a small or absent eye. There may be extra fingers and toes. Now, Patau syndrome, remember, is a trisomy 13. And it's really very devastating and very scary condition. So I couldn't even put a picture over here to show it to you, but you can Google it yourself. Now, what we talk about when we have extra autosome, right? Chromosome 13, extra chromosome 13, extra chromosome 18, extra chromosome 21. Now, what happens if we have extra X chromosome or extra Y chromosomes? The ones that we call sex chromosomes. Now, people with sex chromosome and euploid have extra or missing sex chromosomes. Some conditions can result from non-disjunction in meiosis in the male or female. Sex chromosome and euploids are generally associated with much less severe symptoms and characteristics than autosomal aneuploids. So that means if we have extra X chromosome, we will not have that severe devastating consequences. All right, so now I just want to remind you that during sexual development, females produce female gametes that are called eggs. So all eggs always carry 22 autosomes. That means chromosome 1, 2, 3, 4, 5, so on, chromosome 22, and 1 X chromosome. So we never have eggs. Well, only if it's normal egg, if it's not affected, if it's have euploidy, it's going to be 22 autosomes and 1 X chromosomes. So here's normal oocyte. So it has X here, so it only can have X. Normal sperm will have 22 autosomes and either X or 22 and Y, right? So that's the So if you're female, all your eggs have like one X chromosome. So you really have no control on is baby gonna be a male or female. You always give your child an X chromosome. Now your partner, your husband, your boyfriend, they have about 50% of sperms that carry X chromosome and 50% of sperms that carry Y chromosome. And when one of these, if this sperm fertilize an egg, then it's going to be a girl. If this sperm fertilize the egg, then it's going to be a boy. So that's a normal sperm, and it's going to be normal is a male or female. And look how we abbreviate the genotype, 46XY or 46XX. Now if we have any abnormalities, for example, we have two X chromosomes in egg, or we have two X or two Y chromosomes in sperm, then it's going to be all different consequences, and that's going to be all Euploids, and Euploidy will include over here sex chromosomes, right? So let's look at the example of non-disjunction that leads to sex chromosome aneuploids. So the first is a Turner syndrome, and if you look over here, Turner syndrome is X0. That means one X chromosome is missing. So it's about 1 in 2,500 female birth. 99% affected fetuses die in utero. So most of the babies will die before they have chance to be born. If they are born, they will have very specific features such as short stature, webbing at back of neck, incomplete sexual development, they cannot have kids, impaired hearing. Individuals who are mosaic may have children, and mosaic means if not every single cell in their body missing X chromosome. So some cells missing X chromosome, some don't. That's what mosaic is. So then they might have kids. So that's monosomy, right? So we have one X chromosome instead of two. Klinefelter syndrome, and karyotype is XXY. So you can see a person has extra X chromosome. So it's a male. It's about 1 in 500 male births, and feature will include incomplete sexual development, rudimentary testes and prostate, long limbs, large hands and feet, some breast tissue might develop as well. It's the most common genetic and chromosomal cause of male infertility. So that's a trisomy. We have extra X chromosome. Jacob syndrome, XYY. You see here, one extra Y chromosome. 1 in 1,000 male births arises from non-disjunction in a male, producing a sperm with 2 Y chromosomes that fertilize normal oocyte. 96% are phenotypically normal. So now you can see here how really the alternation in a sex chromosome doesn't have that huge drastic effect on phenotype. 90% have normal phenotype. Some modest features include like great height, acne, speech and hearing disabilities. Before, they suggested that those people are more aggressive, but the new studies on aggressive behavior did not support that statement that those people are more aggressive because of one Y chromosome. That's not true. Right. Okay. So that's pretty much what we cover over here with some example. That was abnormalities in number of chromosomes. So we'll go back over here, and so it's a numerical abnormalities. Now we're gonna look at structural abnormalities. When we have 46 chromosomes, but those chromosomes just missing the parts or have extra parts and so on. So here's our chromosomal abnormalities. So the first diagram show you the normal sequence of genes, right? So for example, we have this chromosome and we have genes A, B, C, D, E, F, G, H, I, J, K, L, M, N, right? So that's just the genes located on the chromosome, normal sequence. Now we can have deletion. So you see these genes D, E, and F was deleted from a chromosome. We can have duplication. In this situation, D, E, F duplicated itself. So we have another gene D, E, and F, or we have inversion. And inversion is, see how they're supposed to be in order A, B, C, D, E, F, but this, it was a breakage in the chromosome here and here, and then it just flipped 180 degrees, and that's what inversion is. So that's all chromosomal abnormalities that related to shape of chromosomes. Okay, so the first is deletion. Missing genetic segment from a chromosome, often not inherited, and rather they arise de novo, that means in new mutations. When we have a larger deletion, they increase the likelihood that there will be an associated phenotype. An example is karyotype syndrome, deletion on chromosome number 5. So here's the model that show you deletion of segments. So that's a normal chromosome, and then this segment that carry, segment D is just deleted. If it's a small deletion, it might not affect phenotype, but if it's a large deletion, that it will. Duplication. So in a duplication, you can see here how segment B and C was duplicated in a chromosome. Presence of an extra genetic segment on a chromosome, often not inherited, also arrived de novo. Effect on a phenotype is generally depends on their size. So again, if it's a small segment that is duplicated, that it might not have effect. But larger duplication tend to have an effect, while smaller ones do not. So that's a duplication. Then we have translocation, when two non-homologous chromosomes exchange segments. Now, what does it mean non-homologous? Because remember, you have a pair of chromosomes. You have, let's say this is chromosome 1, that's from dad, and a chromosome 1 from mom. Those are homologous chromosomes. Right, so both are chromosome 1. Right, so that's chromosome 1, and this, let's say, chromosome 1 prime. They can exchange segments. Right, so they can exchange segments. That means they can be like this. So I can have, let's say I have, oh, I didn't want it to be, I want it to be blue actually, but for some reason it doesn't allow me to pick up blue. Yeah, okay, so it might be, for example, here gonna be blue, and this part of the blue will be right there, and then we can have a red one. So this is exchange between homologous chromosomes. Chromosome 1, mom chromosome 1 and dad chromosome 1 can exchange segments. That's interesting, right? But we will discuss it more when we talk about meiosis. However, if we have, for example, chromosome, if you have chromosome 14, right? So for example, this is chromosome 14 from dad, and this is chromosome 14 from mom, right? That's chromosome 14. And then we have chromosome 21. It's a smaller chromosome. Here's chromosome 21 from mom, and here chromosome 21 from dad. Why I'm so bad at changing colors? I know that's right. It upsets me too. Come on, I need blue. See, that's something. Doesn't allow me to pick up blue stuff. Why? Oh, here. The chromosome 21 from a dad. Now, if we have exchange between chromosome, for example, 14 and chromosome 21, right? Then this is called non-homologous chromosome. So chromosome 14 and chromosome 21, they are non-homologous. So if we have exchange between non-homologous chromosomes, then it's called translocation. Translocation can be inherited, because they can be present in carriers, now can be present in mom or dad, who have the normal amount of genetic material, but it just rearranged. There is two types of translocation. Robertsonian translocation, the transfer of genetic information in one direction, and don't worry, I'm going to show you a diagram, and reciprocal translocation, when portion of two chromosomes are simply exchanged with no net loss of genetic information. So let's look at two types of translocation. So you see how over here, let's just ignore one, let's just look at B. So here's our chromosomes. We can say this is chromosome, I don't know, 10, and this is chromosome 18. Just give them any number because they're not homologous. Homologous chromosomes, they look the same and they carry the same genes. This is different chromosomes. So you see they have different genes. Now, this chromosome has segment B and C, and it just translocated to this chromosome, to another chromosome, right? So this is called non-reciprocal translocation or Robertsonian translocation. So that's example of Robertsonian translocation. When we have reciprocal translocation, we actually just switch segments. Segment of one chromosome goes to, let's say, this M and an O segment goes to this chromosome, and A and B segments go to this chromosome. So we kind of like, we have the same genetic material, right? They just located on the different chromosomes. So that's a translocation. So translocation can cause syndromes. So they can cause genetic condition. Like 5% of Down syndrome result from Robertsonian translocation between chromosomes 21 and 14. It tends to recur in families who also have more risk of spontaneous abortions. One of the parents is a translocation carrier, may have no symptoms. The parent may have no symptoms, but distribution of the unusual chromosomes lead to various imbalances. So let's look how Down syndrome can be caused by translocation. So here's we have a mother, and as any person, remember we have pair of each chromosome. So she has two chromosomes 14 and two chromosomes 21. But now look at a father. Father has one normal chromosome 14, one normal chromosome 21, and one chromosome that is actually combined two parts of chromosome 14 and 21. So what happened, this piece of chromosome 21, let's put father, this piece attached to chromosome 14, and those little segments were lost. And little segments, when they were lost, they do not carry that many genes. So the Mr. P doesn't have any changes in phenotype, so no any symptoms. That's just a normal guy, right? And nobody would even know that he has this karyotype, because he still have 214 and 221, right? But when mom make an egg, this chromosome split and this chromosome split, right? So this is the mom egg right there. So let me now use it. So that's a mom egg. That's a normal egg. Mom always gonna make normal eggs. So see, that's mom's egg, this mom egg, here's a mom egg, that's a mom egg or ovum, right? But when dad start making sperm, right? How you split this? It can be split in a different in different pattern. So dad might split over here. So these two chromosomes go to a sperm. So here's dead sperm, and that's a normal sperm. So if this sperm fertilizes the egg, it's gonna be balanced normal karyotype, right? Because baby will have two chromosome 14, two chromosomes 21. But if it splits this way, one sperm will have two chromosomes and one sperm will have this chromosome that is kind of recombination of two. So here, look, that's a sperm, another sperm shown over here. And if this sperm fertilized egg, it's still gonna be it's going to be balanced translocation, but this person going to be a carrier. So this person going to be exactly like that. But if it splits, now let me clear everything. Now let's see if it splits over here. Right? If it splits over here, look, that's mom's egg, still normal. But look at this sperm over here. That sperm has, so we split it this way. So it has chromosome 21, and it has chromosome 14, and another piece of chromosome 21. Now, this is our Down syndrome, translocation Down syndrome, because we have 2 chromosome 14 and 2 chromosome 21. Now, the rest of these possibilities will cause spontaneous abortion, right? But because it either will have extra chromosome 14 and baby will not survive, or it will be missing chromosome 21, or it will be missing chromosome 14. Neither one is the conditions that allow fetus to survive. But we just looked here, the example how Down syndrome can be caused by translocation. So this is the one that runs in the families. Another type of Down syndrome that caused by non-disjunction, that's a new mutation that arises. Right? It doesn't run in the families. Okay. Another chromosomal change in the shape of chromosome is called inversion. Now, chromosome segment that is flipped in orientation. About 5 to 10% cause health problems, probably due to disruption of genes at the break points. And we have 2 types of inversion, paracentric and pericentric. Inversions with devastating effects can be traced to meiosis when a crossover occurs between the inverted chromosome segment and non-inverted homologue. Now, if you didn't understand, let's look at the this diagram here. So, so what is inversion? So, what is paracentric? Centric means this centrosome, and paracentric does not include centromere. I'm sorry, centromere. So here's the centromere, the more constricted part of chromosome, and if inversion doesn't include it, this part, it's called paracentric. So you see genes A, B, C, and D. Then the cut was made over here, cut was made over here, and then the segment was flipped. And here's our result. So now we have A, D, C, B, and F. So we have the same genes, really, but they just, you know, they pretty much they in a different order, but they're still present. Pericentric inversion includes centromere. So the cut in chromosome was made here and here. Then this segment was flipped. And again, we have a wrong sequence of the genes. So we have A, B, C, and then instead of D, E, F, and G, we have F, E, D, G, and H, right? So again, we still have the same genetic material, just rearranged. Right? So that's what inversion is. And inversion can cause problems if cut made through a gene. For example, you see, like, oops, if we cut right in the middle of a gene, then of course the gene is destroyed and you flip it over, you don't have a functioning gene. Or even a position of gene on a different part of a chromosome can affect the phenotype of a person. And that's what inversions. And next we have we can have isochromosomes. So that's also genetic condition that caused by a change of a shape of a chromosome. Isochromosome is a chromosome with identical arms. So look over here. That's our normal chromosome over here that has genes A, B, C, D, E, F, and G. And see how it has 2 arms. So this arm will have the same gene. So we will have again A, B, C, D, E, F, and G. Right? Now, when chromosomes split, right? So when we create a egosperm, chromosomes must divide right in the middle over here, right? So that's our normal chromosomes that we need to produce. So one chromosome A, B, C, D, E, F, and G, and another chromosome is A, B, C, D, F, G. Isochromosomes are formed when centromeres divide along the incorrect plane during meiosis. So they divide this way instead. And now look what we have. We have ABC and we have CBA. That's our genes. So that's our duplication of genes. And over here, we have duplication of some genes and deletion of others. So we missing here gene A, B, and C, and over here, we're missing gene D, E, F, and G. Now, how it would be important? Well, let's imagine, just for example, that genes A, B, and C needed for eyes to be developed. Now that the person doesn't have instruction how to develop eyes, or maybe D, E, F, and G, those genes are needed for embryo to develop its heart. So the baby cannot be born without heart, right? So it's just exaggeration, but it just shows you if you're losing some genes, it might be like very, very serious. And it is very serious. And most of those embryo will never develop. They will just be aborted. However, we do have some isochromosomes. They are known for chromosome 12 and 21, and for the long arms of the X and Y chromosome. And if it says that it's known, that means those babies was born with this type of abnormalities. Ring chromosomes. Ring chromosomes can be created when telomeres are lost, and telomeres are those end parts of the chromosomes, and then chromosome end parts became sticky and fuse, and gene can be lost or disrupted, causing symptoms. So here's a normal chromosome, here's the ring chromosomes, occurs in one in 25,000 conceptions. And here, uniparental disomy, another chromosomal disorder, abbreviation UPD. It's an inheritance of two chromosomes from chromosome parts from the same parent. That's what uniparental disomy. Now remember, disomy is a normal condition because we have disomy for chromosome 1, for chromosome 2. That means we have a pair of chromosomes. You cannot have one chromosome 5. You always have two chromosomes 5, right? So disomy is normal, but the difference is that I get a chromosome 5, for example, that's a chromosome 5, and I get one chromosome 5 from my dad, and I get another chromosome 5 from my mom. That's how it's supposed to be. So that's a normal, regular disomy. Now, if somebody has, so I'm trying to, I cannot pick up blue color again. If somebody has two chromosomes 5, seems like, okay, that sounds good, right? Chromosome 5 and chromosome 5, but both comes from mom instead of one comes from dad. So that's a normal. This is not normal. So instead of one coming from dad and one coming from mom, both come from your mom or both come from your dad, then it's called uniparental disomy. And again, what does it mean at uniparental? Uniparental means it comes from one parents, right? That makes sense. Comes from one parent. Many of the cases probably never seen. That means that the embryo was aborted at an early time, and we never really see it. But we do have some disorders that can caused by uniparental disomy. So this diagram shows you So here's, for example, father, and it has some mutation in one homologous chromosome, and mother has a mutation. So the baby can receive two genes, both are mutated, and it will cause some disorder. However, we might have the father who is not even carrier and mother who is carrier, and how the baby get this two copies from mom, right? That's what our uniparental disomy is. Well, because, and if you wonder how I can go two from one, because before the cells divide, they need to duplicate their chromosome. So you duplicate this chromosome and you inherit both copies of affected gene, right? That's what this condition is about. Uniparental disomy causes symptoms if it creates a homologous recessive state associated with illness, or it affects an imprinted gene. So here's the examples that were studied. Example of uniparental disomy: a woman with cystic fibrosis that inherited two copies from her mother's chromosome 7 and neither of her father's. Some children with the Prader-Willi syndrome have inherited two chromosome 15 from their mothers, and some children with Engelham syndrome have inherited two chromosome 15 from their fathers. So a few examples, but they do exist, right? Okay, so I think that was our last slide. Okay, so I just want to remind you that we cover chromosomal abnormalities, and that we have two types of chromosomal abnormalities. I'm trying to go back to show you either numerical abnormalities or structural abnormalities. Okay, well, thank you for watching, and I hope it was helpful.